Hey everyone, welcome back, and today let's solve Leetcode problem 2658, titled Maximum Number of Fish in a Grid. So we're given a zero-indexed 2D matrix of size m by n, where our C basically is an indice or cell value that represents either a land cell if grid at index RC is equal to 0, or it's going to be a water cell if grid at index RC is greater than 0. And that means it would also contain a fish for that specific water cell. And a fisher can start at any water cell R, C, and do the following operations any number of times. Either he can catch all of the fish at RC, or he can move to any adjacent water cell. And when they mean adjacent water cell, they mean the four directionally adjacent water cells, which either means up, down, left, or right, the four cardinal directions. And we need to return the maximum number of fish that the fisher can catch if he chooses his starting cell, RC, optimally, or simply just 0 if there are no water cells that actually exist. And to kind of reiterate, this an adjacent cell is defined to be the four directionally adjacent cells, either up, down, left, or right, RC plus 1, RC minus 1, R plus 1C, or R minus 1C, if it does exist. And when they say if it does exist, they really mean if it's in bounds of the matrix, meaning we don't have any too large indices that are greater than the dimensions of the input grid, and we also don't have any negative indices that are less than 0. So in example 1, we have a 4x4 input matrix, or I should say grid rather, and in this case, our output is 7. And the reason why is because the most optimal cell to start from would be at cell 1, 3. That is R, 3, which means kind of like coordinates x, y, 1, 3, right? And after we actually collect 3 fish, we can actually then move to 2, 3, and then we can collect 4 fish. So we start at 1, 3. Keep in mind 1, 3 would have 3 fish, and then we move to 2, 3 to then get 4 fish. So that would be 4 fish right here, right? And that is the most optimal solution. We wouldn't be able to go anywhere after collecting that 4th fish, and so 7 is the maximum amount of fish we can actually get. Think about it. If we start from 3, we can go to 2. There are no other 4 directionally adjacent cells, so there's 2 to have more fish, and no other selecting cell would actually be more optimal than that. We can go through every single cell and possibly start it exploring all its four adjacent cells recursively, and 4 and 3 would be the optimal pattern to choose from, starting from 3. So in example 2, we have a lot more unique of an input. We only have 2 cells with fish. All the other ones are simply just land cells. And in this case, of course, our output is 1. Either we can start at the topmost cell or the bottom right cell. And either way, we can only get that singular fish at that specific cell. There isn't anything else we could do because they're not 4 directionally adjacent to each other. There's no way we can get to both of them because there are land cells in between them. And finally, for the constraints here, we see that m and n are the grid, or rather the number of rows and columns respectively of the input grid. They're both within 10, and they're also going to be given that grid at index ij is not going to exceed 10 either. So very, very small inputs kind of tells us that we don't have to have the most fastest of algorithm, and in this case, we kind of really don't, at least relatively. And so, if you guys haven't realized yet, this is actually a recursive problem, right? We literally start at every single possible cell as a possibility and literally just recursively explore all its 4 directionally adjacent cells and check which starting cell is the most optimal. In other words, which starting cell has the maximum return or result value, right? And that is the literal entire solution. That's it, right? Basically, really, we have to just explore all the connected cells starting from any cell in the fish, and it really is just basically on a high-level rundown, a graph traversal problem where we can solve it using the depth for search, or the DFS algorithm. Right? Effectively, we're going to explore connected components in the grid, and we'll do this by first traversing every single cell in the grid, and if the specific cell actually does contain fish, meaning its value at that cell is greater than 0, we can perform a helper DFS recursive function to actually collect all of its fish in the connected component. And effectively, while we're doing that for every single iteration or every single possible cell to start with, we have to track the maximum fish count that we actually encounter during all of the DFS traversals for all of the cells, and we can explore all of the cells simply using nested loops in Python. Right? Effectively, again, we're going to use that recursive helper function, DFS, and we're also going to keep a visited array to avoid revisiting any cells in the same connected component, and we're also going to update a max fish variable that's literally just going to store our return. It's the largest number of fish we can collect starting at the most optimal starting cell. right? So with the high level rundown out of the way, let's go ahead and dive straight into the code here. So what I usually like to do for matrix problems is actually get the number of rows and columns of the matrix and store it in two integer variables, rows and columns. And the way we can do that in Python is simply get the length of the grid and the length of the grid in index 0. This is a pretty neat way to get the number of rows and columns of an input grid, basically to help us iterate over the grid later on and help us traverse the grid staying within bounds for all the possible starting cells that we choose. So now let's actually initialize the visited 2D array. I'm literally just going to call it visited, and again, it's going to be a 2D array, meaning it's going to be basically a Boolean value, false, and I'll do something a little bit different this time in Python. It's going to be false for, I'll just use a blank iterator in this case, in the range of the number of columns. And the way you can actually structure this outside of this array here, you can actually put that in the range, so in the range of the number of rows. And just double checking that this is the right syntax here, give me a minute. But I do think this should be right. Don't think we need that. But yeah, that should be it. False in the range of the number of columns. Okay, that's good. Okay, so basically again, what is the purpose of this 2D list visited? Basically, it's going to have the same dimensions as the grid, and each cell in this visited would be initialized to false, right? That means that we haven't actually visited any cells yet. And effectively, we're going to update this every single cell accordingly during our DFS algorithm to actually avoid revisiting any cells, right? This is literally just marking if we've actually visited any cells in specific paths or 4 directionally adjacent cell paths that we're checking starting at every cell. So for example, take example 1 for case, we'd have an outer loop here and an inner loop here, iterating through every single cell for every row and column in this input matrix. Let's say our current cell is 2. Right, we collect the 2, we go to the 4 directionally adjacent cell 1. Now we collected the 1. Both of these cells would then be marked as true because we have actually visited them in this specific path. In the next iteration, when we actually get to the 1, we don't want to revisit it. Why? Because we already know its path ends there. We already know that it's connected to the 2, and our maximum fish from this specific path is 3. We don't care about doing it again, because we know it's connected to the same path as 2, and this is where that path ends, with a fish for this specific 2 starting cell as 3. That's the entire reason why we have to use this visited cell to avoid any redundant checks for paths that we've already visited for the starting cells, right? And we're going to update this as we actually traverse through the grid during our BFS to avoid revisiting any cells that we've already checked. Okay, well, now let's actually initialize that recursive helper function DFS. I'm literally just going to call it DFS, and for its parameters, it's going to take 2 values, of course, R and C. These are literally just the parameters, if you will, R and C. These are the indices or cell values in the grid for this specific iteration, right? And the first thing that we're going to check is actually, is our current index or cell value RC, is it out of bounds? And a way to do that in Python is, it's pretty lengthy, but I'll kind of explain it as we go. If R, that's going to be a row value, if that's less than 0, meaning it's negative, or it's greater than the number of rows we even have, we know that the row value is out of bounds for this current cell, or similar logic here, or the C value, that's the number of columns, if that's greater than the number of columns we even have, or equal to, or C is less than 0, meaning it's, of course, a negative index which we can't have, or grid at RC, if it's actually a land cell, meaning if it's actually equal to 0, we know we can't do anything with it. And the next thing we have to check, well, what if it's equal to negative 1? So we'll have another OR condition here. If grid at RC, if it's equal to negative 1, and finally, we have to check, or what if we've already visited it? And the way we can do that in Python is or visited at RC. If either one of these conditions are true, we know we immediately have to simply return 0. This is the kind of base case here. It's basically the in boundaries check, right? It's going to take parameters R and C, and it's actually going to kind of use them as the current row and column indices. We're checking A, if we're out of bounds for the current row or cell value. We're also checking if the current cell is a 0, meaning it contains no fish, or it's a negative 1, which means it's impassable. And we're also going to check, is the current cell, has it been visited yet? And that means if visited RC is equal to true or false. And if any of these conditions are true, we return 0 because there are no fish to collect here for this specific iteration in this specific cell. However, if we're still going on with this iteration of or call of the function, if we haven't returned false just yet, that means none of these conditions are true, and we can actually use the cell and mark it as visited. So we'll set visited at RC to be true, meaning we are actually using it for this specific iteration, marking it true if it's actually valid and starting to use it in this iteration. So the first thing that we have to do is actually initialize our fish count. That's going to be the number of fish we actually collect. And it's going to be initialized to the current cell, graded RC, whatever value it actually has. for that number of specific fish. There's going to be the number of fish in the current cell, and that's going to be a grid index R, index C. And this is where we actually have to have a recursive part of our code. This is where we actually go through all the possible solutions and increment our fish count for every single 4 directionally possible cell for that specific path. So we'll increment fish count by these 4 directionally adjacent cells for the recursive helper function. The first one is going to be DFS at R plus 1C. The next one is going to be DFS. In fact, I should probably copy and paste this because it is pretty redundant, but whatever. Fish count plus equal DFS at R minus 1C. And the next thing we actually have to check is the other C values. So fish count plus equals, DFS at R C plus 1. And finally, we'll have fish count to be incremented by DFS at R C minus 1. Those are literally just the 4 directionally adjacent cells. And to put this in context, imagine our current starting cell, RC, is this 0. We'd explore this 3, we'd explore this 1, we'd explore this 0, and we'd explore this other 0, and keep going recursively for those nodes, specific 4 directionally adjacent cells, until our path is completely done, and we don't have any other cells or we're out of bounds to actually check and collect fish for. That would be our current path, assuming that this 0 is our current RC or our current starting node. Right? And effectively, we simply have to return whatever fish count we actually end up with. So return fish count for this specific path, starting from this specific cell, index R, index C. It's going to be returning the total fish collected from the connected component starting at the current cell, if it's actually the most optimal, index R, index C. And now let's actually have the main traversal logic to go through every cell and check if it's actually the maximum value or the most optimal cell to start with. So I'm going to initialize a max fish. It's basically going to store our return. It's going to keep track of the maximum number of fish collected across all the connected components, starting at the most optimal cell for every single cell in the input matrix. This is our return variable. So now let's actually go through every cell and actually accurately determine if it's the most optimal starting cell. So for R in the range as our outer loop for the number of rows, and for C in the range of the number of columns. Now, effectively, what we're going to do is, if grid at RC, if it actually does contain fish, meaning it is actually a valid starting cell, so if grid at RC is not 0 or -1, meaning it's just greater than 0, and we haven't actually visited grid at RC just yet, meaning it's not visited and it actually does contain fish, it's not -1 or empty, meaning a land cell, we can set max fish to be the maximum of course itself, because we don't want to make it smaller of what we've recorded so far. And if we start at this specific cell for its path RC, so DFS at RC, assuming RC is the current starting node that we're going to try to check to see if it's the more optimal solution. Effectively, once this for loop is done executing, once we've actually looped through all the cells using this nested loop in our input grid and checking if it's actually the most optimal starting node to have for the number of fish for that connected component, for that path, we simply have to return whatever our max fish is, right? It's going to actually store our result. It's going to contain the largest number of fish collected from any connected component in our grid for any starting cell. And again, to reiterate what we're really doing from line 16 to 19, effectively we're iterating over each cell in the grid. And if the cell contains fish and it actually hasn't been visited yet, we can call DFS starting from that cell, and the result of that DFS is then compared with the max fish, and we update the max fish to whatever the larger value is accordingly. So if I were to submit this code, this would actually be accepted, and this would be a valid solution. Sorry. Looks like I forgot to close something here. Let's just check it out here. Sorry about that, guys. We should close this. Now this should be accepted, and this should be a valid solution. Let's just go ahead and double check. Okay, let's see what I did wrong here. Probably some really simple edge case here. It's going to be false in the range of the number of columns. Okay, I'm just going to retype this, guys. I think it's easier for all of us here. Basically what this is it's going to be false, and it's going to be in the range of the number of columns, right? And this is going to be in the range of the number of rows. And this should actually be in curly brackets. So now let's go ahead and check if this works. Sorry about that, guys. And this should actually not be there. Sorry about that. Now this should be accepted solution. Now this should actually work. And as you can see, this is really just about as efficient as you can get. So feel free to just fast forward that part. Sorry for not telling that before. But really, to kind of reiterate what this code actually does as a whole, effectively, once we actually initialize our number of rows and columns and our visited array and our DFS helper function to actually explore every single recursively explore every single 4 directionally adjacent cell from every single potential starting cell, we basically then iterate over every single cell in the grid, and for every unvisited cell with fish, we're going to use our DFS helper function to actually explore all the connected cells and collect fish recursively for that specific path, checking if the current cell RC in this nested loop is the most optimal cell to start with, and we're also simultaneously tracking the largest number of fish collected during all of the DFS traversals and returning that value as a result, which we store in the max fish variable, right? So for the runtime complexity, this is actually going to be a big O of m times n. Runtime complexity, m is going to be the number of rows, and n is going to be the number of columns. Why? Because really, we're just visiting every single cell at most once in these nested loops here. That's kind of our bottleneck. And for the memory or space complexity, it's also going to be big O of m times n, because we're literally using this visited 2D array, which has the exact same dimensions as our grid, m times n, and our recursion may go as deep as the number of cells in the worst case. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.